Hi everyone, I made this video to delve deeper into Basic09 I Code. It is important to understand how Basic09 compiles the code and creates the data storage. As I progress through this video, I will be including commentary not found in the notes. I created a small procedure to illustrate the I code generated by Basic09 and packed into an executable module. While the source code is compiled when Basic09 loads it, only the packed code presents itself for inspection. The procedure is named sample. The 4 comment lines at the top were not included in the file when I loaded it into Basic09, so the unpacked proc size doesn't include them. The data size doesn't change between unpacked and packed code. So let's look at the source code. These are the 4 comments that are not included in the copy that's on VCC. So you'll see that the unpacked code is 792 bytes, the packed code is 512, and the data size is 374 bytes. So opening Basic09 with 8K is more than enough to be able to hold the procedure and run it. So I include in there a type statement for the registers and a variable dimmed to that type, as well as the call code and 32-byte packet byte variables, and then a path byte and a path open boolean, a file pointer, a counter, and an error variable that are integers, a real variable, and a string variable of 255 characters, and then a parameter string of 80 characters. Then the first thing I do is run a syscall that enables me to get a sample of a run statement using a named subroutine. And then I do my initial initializations. And here you'll see these two, another real and another string. Now, some people might say another string $. When it's used in Basic09 as part of a variable name, it is a string variable. That's why I say string. Okay? I could have just said another $, and then just said another string, but I wanted it obvious that it was a string variable. Okay? Another real is, both of these are defined by use, and what they indicate is that these variables do not have a dimension statement. So Basic09 is considering this one to be a real because it doesn't have a $, and this one to be a string because it does have a $. So after that, I have the onError goTo to give an example of a line number reference. And then this performs the loop of opening the file and then reading the contents of the file, and then after it's read the last line, telling you how many lines were in the file. Then it closes the path and sets the boolean back to false and ends the procedure. Then the error trap is at line 1000, and it only checks for 2 errors. 216 if you specified a file path, but that file does not exist, or a 56 error if there is no parameter. Those are the only 2 errors that it handles. So if you specify a file path to a file that is not a text file, you're going to get unexpected results. But after that, it prints the error and ends the procedure. So that's the sample procedure. And over here in Basic09, we can list the procedure, and you'll see it's the same thing. Okay. And it is 792 bytes with a 374 data size. Now over here in this window, I did an ident on the packed module. You can see it is 512 bytes in size, and it is a good module. So now I can run this. And I'll use its own source code file as the example. And it lists the file. Now the loop in there, the for next loop, is slowing it down so you have time to read each line and it'll at least know what it says. So this is just showing that it actually is a working procedure. It's not just some crap code that doesn't do anything. Shows that there are 49 lines in the file video/sample B09. So we come back over to here, and then we come back over to here. Now, back to the notes. Once I packed the procedure into a module, I performed a dump of the module, redirected to the file sampledmp.txt. On my PC, I renamed the file sampledmp.tak, as that extension allows me to add color highlighting to its content. Using the source code file and the dump file, I created sampledump.txt. I also renamed it to sampledump.tak so that it would be easier to tell things apart. This file breaks the I code down into specific instructions and other data and inserts the corresponding source instruction immediately before the I code instruction in the I code area of the module. So first I'm going to show you what the dump file looks like. This is the way the dump utility in OS 9 creates a dump file, in case you don't know. And then this is the dump file I created. So you can see I put the name of the procedure up there, and then I put in the module header. Then I define the I code area, and I put in the source code instruction followed by the I code instruction that includes a relative offset address. All addresses in Basic09 are relative. So relative to the I code area, relative to the description area, relative to the symbol table. So then you notice down here, this is your on-error go-to. 010D is the offset address relative to the beginning of the I code area for line number 1000. Okay. Come down here to, went too far. It's to right here. This is line 1000, error equals error. This is the I code. And you'll notice the address of this statement is in the I code is 010D. And it is. Okay. So then after this, and you can study the file I uploaded to Discord to see how I code is actually structured. So I'll give you a little overview. 80 is the token for a byte variable. 0020 is the data storage memory address for where that variable's storage occurs. Now, there are 3 places that get pointed to in the instruction area. 80, 81, 82, 83 point to data storage memory. 84 and 85, well actually 84, let me find one here, right here. that is a string variable, and it points directly to the description area. That is the address relative to the beginning of the description area where the shape for this string occurs. 85 points to the symbol table, and this is the offset address relative to the beginning of the symbol table where the entry for this variable is. And when we get there, I'll show you that it actually points to the description area. So 23 is the token for run, and 0012 is the offset relative to the beginning of the symbol table where the entry for this named subroutine occurs. So, and just so you know, 80 is byte, 81 is integer, 82 is real, 83 is Boolean. So, strings are denoted by 90 and FF. You can call this the beginning quote and this the ending quote. Reals are defined by 8F. 8F is the token for a real constant or real literal, as I've called them. 8D is for a byte literal or byte constant. 8E is for an integer constant. And 91, I believe it is. Let me see, it's up here somewhere. Yeah, 91 is the token for a hexadecimal integer. So, the rest of it you can pretty much figure it out by studying this file. So we come down to the description area. This occurs immediately after the last instruction. There is nothing to indicate a separation. What there is up here in the header. You have these addresses, 001F, 0176, 01E1, and 01B7, and 0174. Okay. So this is first executable statement address. I was previously of the opinion that it was something else, but apparently it just is the relative offset to the beginning of the I code area. This is the first data statement address. If your procedure includes data statements, this is where restore without a line number will restore to. After that, restore with a line number will restore to a numbered line that is a data statement that corresponds to the number in the restore statement. So anyway, there's 0176, 01E1, and 01B7, and 0174. So we come down here. This is 96, 97, 98. So the description area begins at 0199, or 0198, excuse me. I don't know why that's not correct. I'll have to check that out and see what's going on there, but that's what the header contained. But if you look, oh, no wonder, I've got it wrong. It's 76. Oh no, it is 96 because of that. Yeah. Okay, so I don't know. Oh, okay. Well, no, it is module offset. Oh, yeah, module offset. The module offset is not the same as the relative offset. So the number points to here. I can't remember which one's which, but one of them points to here. One of them points to here. Anyway, so at the description area, we have the shape data for the type statement. Okay. And this is how it breaks down. Now this I don't know if it's an integer or 2 bytes, or if this one is a byte and this one is part of this. If it is, then this one has a weird value that I'm not sure what it is. So the way I've been doing it since I started writing DCOM is that I have just seen this as an unknown integer. Okay. So I have it over here. This is an unknown value. 06 is the first field, CC. So you notice all the other fields are integers. But it's CC, A, B, DP, X, Y, U. Okay. Total size, 10 bytes. And the total number of fields, 1, 2, 3, 4, 5, 6, 7. Okay. Now this one is the register statement, the reg statement that is assigned to this type. The only thing that occurs here is its size. The size agrees with that size. It's the only type statement in there, so that proves that. Now coming back up here to this 850006, we come down here to the symbol table. 0006 is 650011. In the symbol table, values between 60 and 7F are variables. 40 and 5F are field variables. 80 and 8F are 80 and 9F are parameter variables, and then A0 and higher, or A0, and every name subroutine, no matter what it is, begins with A0. And that's the highest that it goes. Okay, so you notice 0012, the run statement, 230012, so that's where that points to. This one, 0016, points to 0011, which is up here. So that point, the instruction statement pointed to here. The symbol table entry points to here. And this is the same with records and arrays. Arrays will point to here, which will then point to here. Strings will point to here directly unless they're parameters. Okay, parameters point down to here, and if it's a parameter string or a parameter record or a parameter array, it points up here. So you notice this one, the parameter is a string. 84 is the code for parameter string. Points to 001F. 001F is right there. Points to data memory address 0176. It is 50 bytes in size. However, that is not what's at that address. What's at that address is this. It's a integer pointer that points to where the syscall routine resides, or the syscall subroutine, I should say. Okay. And you notice it points to 1074. 1076 is here, and it's 4 bytes. Because it is also a pointer, but it's a pointer that points outside the process space, or out of the procedure space anyway. So there's, oh yeah, you can tell by the entry here, 04 or 174 to 175 is 2 bytes. 176 to 179 is 4 bytes. Okay. So, okay, so yeah, that's what those are. This is the pointer to the named subroutines, and this is the pointer to the parameter. Okay. Both of these are in data memory. So B7 and E1 are the description area and symbol table. Now I don't know why it points to the symbol table first and then to the description area, but that's what it does. So, oh, and everything from here to here are, or it might actually be to there, are header extensions for Basic09. From here to here and here. Actually, that might be part of the, I think that is part of the default header. To there is the standard module header. Everything between there and there are Basic09 module header extensions. So now down here, as I said before, these are field variables. This one points to position 1 within the regs variable. Okay, but I have a note over here, field offsets start at 0. So what's missing? 400000, which is CC. 400002 and 400003, which are B and DP. And 410006 and 410008, which are Y and U. The reason they're missing is because they were not used. Any variable or field variable or even a parameter variable that is never used, because of parameters, the parameter will still exist in the data memory at the parameter address. But because it's never used in the source code, there won't be, it won't occur anywhere in the I code area. Okay. For the rest of them, if they don't occur here, they don't occur in the I code area either. Well, that's not true. Some things can occur here, or can occur in the I code area and not occur here. An example of this is we come back up here to, let's see, file pointer equals 0. 830042 points to data memory address 0042. This does not occur in the symbol table. Okay. 810043 is an integer that points to data storage memory location 0043. It does not occur in the symbol table. Same with this integer, same with this real, same with this real. Okay. So if it's a byte, an integer, a real, or a Boolean in the I code area that is given the token 80, 81, 82, or 83, it points directly to data memory. Now, let's see, I'm not sure, oh yes I do. Down here we have an example of an assignment that assigns to itself. Okay? So 81, which is this file pointer, occurs in data memory. Oh wow, this one's not using. Okay. I don't know why, but this one is this file pointer. It's not using the symbol table. Usually when I run into this entry points to the symbol table. The symbol table will then contain 61 and will point to this address. Now why this one's not doing it, I don't know, but it's not. Okay. Now you'll notice that I include in the memory map this variable. Why? Because it exists in the data map. If you look down here to the data map, you see that 72 and 73 is the to variable in the for loop, and 74 and 75 are the syscall pointer address. Okay? So this one is actually the last variable in the variables section of data memory. So we come back up here to where that was. Yes, for counter. Okay, so this has a data memory address at 172. The corresponding next statement has the same value. So what this is this is the number it's counting to. In the next statement, this is the number it's counting to. Okay. This is the variable that it's being counted, and this is the reference to the variable that's being counted, and it gets incremented okay, this is the number that's being counted to. In this case, it's 10,000. So what happens is when it comes down here to next, it increments this value by 1, compares it to this, unless there's a step value. If there's a step value, it increments it by the step value, which would be here. And up here would be after the 2 and this, it would be 2 this, and then after this would be the token, which is 47 for step, and the value for how many to increase it, which if it's a value no greater than 255, it'll be prefaced by 8D. If it is a value greater than 255 and less than or equal to 32,767, it will be 8E, because 8E means integer. Okay. This is where to go when the for expression is false, okay. Meaning the counter has equaled 10,000. It's no longer equal to 1. It's no longer less than 10,000. That's when the next counter ends. Oh no, this is the next statement inside the loop. I'm not sure what C0 is. Anyway, when it gets done, this is the address to go back to. Okay. Somehow I think that value isn't correct, and I didn't notice the difference. I'm going to have to look in sample DMC, because it should be going here, CF. Okay. Anyway, so that's a for next loop. Now this value right here can contain 4 different values. It's either 0, 1, 2, or 3. If it's 0 or 2, I'll have to look it up to be certain. I think it's if it's 0 or 1, it's an integer. If it's 2 or 3, it's a real. But it might be if it's 0 or 2, it's an integer. If it's 0 or 3, or 1 or 3, it's a real. 1 is, or 0 is next with no step value, or integer with no step value. 1, yeah, I think that's the way it is. 1 is integer with step value. 2 is real without step value, and 3 is real with step value. I think I remember that right. Yeah. Okay, let me look at the symbol table again. there are only three things being pointed to the symbol table in terms of regular variables. The register, the regs variable, 600020 is a byte, the call code variable, and the packet array. So that means it's up here. This is the regs, this is the type, that's A, and that's X. That's regs, and that's call code. And that's packet. Those are the only three things that point to the symbol table. When you come down to the symbol table, 65 points here to 11, 60 points to the data storage location for that byte variable, and 68 points up here to here, which is the shape of the array, and this is the data memory offset of where that variable is. So if you look down here, 21 to 40 is the packet array byte variable. So, hopefully this gives you a little better understanding of iCode. Now this is the memory map laid out just as a series of contiguous locations. I put the registers variable in brackets so you can see that everything from 16 to 1F is fields within the regs variable. Then after that is all the other variables until you get to here. This is the syscall pointer, and this is the parameter pointer. Okay, now down here is where I broke down the regs data to show you which byte location was which variable, which field variable. And then I knew there were going to be some people that were going to want to know what the reserved bytes are. So I have a copy of the original Basic09 header file that was part of the assembly language source code that I received back in, I believe it was 1990. Might have been a little earlier, might have been a little later. I was able to contact Boise Petrie while he was still working at Microware, and he sent me that file. If I had known they were going to use the hard drives that the level 1 and level 2 source code was on for target practice, I would have begged him to give me that source code so I could preserve it. But I didn't know they were going to do that. I found out later they did that, and it broke my heart. The original source code to level 1 and level 2 was shot. Anyway, at least I had the header. Within the header, these are the lines of code that define what those 16 or those 22 bytes are. You'll notice they spelled it PROC3DURE. I think the reason they did that was to avoid the compiler thinking it was the keyword procedure. But I could be wrong. It may have just been a typo. Or they had some other reason for using the 3 there. But what makes sense to me is that they didn't want it being mistaken for a keyword. So, and then you notice it's org0, and then it adds all the bytes, which adds up to 22 bytes, and then it sets the size to the number of bytes, which is 22 if you count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So that's what all I've included in this file. Again, I'm going to have to look at that that one thing to see where it's off, because it shouldn't be, but I think it's just I didn't notice it in this file when I was making corrections. So I'll have to look and see. Anyway, so that's that file. So over here in notes, let's see. Using the source code file and the dump file, I created sample.doctext. This file breaks the I code down to specific instructions and other data, and inserts the corresponding source instruction immediately before the I code instruction in the I code area of the module. After the I code area is the description area, which I named Data Storage Allocation Table, or DSAT, before I knew what microware named it. Following that is the total program variables integer. For reasons I don't know, this procedure shows a total of 22, or hex 16, where decode shows a total of 21, or hex 15 variables. I have to investigate that. I have noticed that sometimes decode's count agrees with this number and sometimes it doesn't, and I'm not sure what the difference is, so I'm still investigating that. Then there's a byte value that always has the value of 03. In one instance decades ago, I had a module that contained the value 04. I lost that module a long time ago and have never seen another module with that value. So I still don't know what that particular byte value is for, or what purpose it serves in I code. Following that is the symbol table, which I named the variable declaration table, or VDT, before I knew what microware named it. Finally, there is the module CRC. After the end of the module, I added more information, which includes the data memory map, a breakdown of the regs variable showing its fields, and finally the code from the Basic09 header file, part of the original assembly source code to Basic09 and RunB, that provides the definitions for the first 22 bytes of the data memory reserved by Basic09 and RunB. To aid in building the data storage memory map, I used decode to unpack the module and copied the sample vars.txt file to my PC, which I also renamed TAK so I could get some colorizing going on. And this is it. These first two lines are basically headers, okay? Except this, which is the total number of variables that were identified. This stands for record number. Each one of these in decode counts as a record. Then this is instruction area, which shows the token that occurs in the instruction area and the pointer. Okay. Next is the description, or the symbol table. If this points to the symbol table, then this is the address at the symbol table, relative to the beginning of it. This is the token that occurs at that location, and this is the pointer to its location in data memory. In the case of field variables, it points to the position within the user-defined type variable of that field variable. And then this is the size of the VDT entry. All VDT entries are 3 bytes, token, pointer, except for the subroutine, which is 3 bytes followed by the name of the subroutine. Okay. Next, we You have the description area, or DSAT. This is the offset address in the DSAT, or description area, where that variable occurs, and that's if. It can be if it either points to here or if it points directly to here, such as in the case of these strings. Okay. If it points here first, then this points to this. If it's this, it points directly to this. So this is the relative offset within the description area. This is the pointer to where in data memory this variable occurs. If it's a field variable, it's the position within the record and its size. If it's the parameter, then it is, where's it down here? It points to here, which points to here because it's a string, which points to here. Okay. For the rest of them, they either point to here and then here, or they point directly from here to here. Okay. So in the case of 80, 83, 81, 82, they're pointing directly to data memory. Okay. Now 850006 and F20006 both point to the symbol table. Okay. So, and that's because 85 in the I code area can be a record, it can be an array. Okay. So in order to determine which type of variable it really is, it points to the symbol table. The symbol table then defines the type and points to where it goes. In the case of records, it points to the DSAT, or the description area. In the case of this, which is the call code, because it's used twice, this one points directly to data memory. Okay. This one points to the symbol table, defines it as a byte, and points to the same memory location. Okay. So that's how to read this file. And you'll notice the order. This is the order that Basic09 stores things in. For the most part, it's the same order that the type, dim, and param statements are in, but not necessarily entirely. For example, the defined by use real and the defined by use string occur here before, the defined by use string and the defined by use real occur after the end of the dimension statements as expected. However, the parameter in the source code occurs here. So Basic09 moved it to the bottom of data, or to the end of data memory. That's where it occurs. Okay. So you're not always going to see an exact match in terms of the order of the variables and the way they were defined in the source statement and the way they were defined in Basic09's data allocation. And over here, there's a few more fields here. VES, TES, and MES refer to arrays. Microware defined a one-dimensional array as a vector, a two-dimensional array as a table, and a three-dimensional array as a matrix. So I've used V, T, and M to indicate one-dimensional, two-dimensional, and three-dimensional. I don't remember off the top of my head why I called it ES. But I did. I'll look it up later and figure out why I called it that. But anyway, there's only one array, and it's the byte one. If it was a two-dimensional array, there would be another value there. If it was a matrix array, there would be another value there. And in the I code, over here, back up in the description area, if this was a two-dimensional array, the second dimension would occur there, the first dimension would occur there. If it was a three-dimensional array, the third dimension would be there, the second dimension would be there, and the first dimension would be there. Okay? And that's the way Basic09 stores them. Now, in addition to that, if it is a record or string array, okay, it will have an additional field that is the size of one element, which is the length of the string or the size of the record. Okay. That only applies if it's a string or record array. Okay. Now over here, this is where I put the string with the number in parentheses that will be appended to the variable name when the source code gets built. So that's what that field is. This field is the variable or subroutine name. Now, decode, as you can see, doesn't have a clue what you called your variables. So it uses its own variable naming scheme. Okay. This here would be blank. I added these so that you would know which one corresponds to what variable. Now down here, this is that to variable, and this is the corresponding variable in the next statement. I indicates that it was determined to be an integer. Okay. R would mean it was indicated to be a real. And if it was as integers, they are defined as 2 bytes and 2 bytes in size. If they were reals, they would be 5 bytes and 5 bytes in size, because that's what they store. Okay. Now then, after that comes the named subroutine, which is syscall. Okay. And you notice its size is only 2 because all it is a pointer. Okay. That's all it is. It's a pointer that points to where okay, somehow I forgot to put that in there. Okay, it did that wrong, but it's not completely wrong. It's still right. It's saying 174 is pointing directly there, which it is. Oh, that's the, okay, never mind. I'm still scrolled over there. So you see, it points to here, A0 points to here, which is data memory, and it's 2 bytes in size. And it's because it is a integer size pointer that points to where the syscall subroutine exists. Okay. On the parameter, it also points to the VDT, which points to the DSAT, which points to data memory, and its size is 4 bytes. Okay. Now the expected size here is the actual size of the data being passed. Okay. This is the long integer pointer that points to where outside of this procedure space this variable occurs. And it's an 80 character string. You notice the string length is over here. So this is a 255 character string. This is a 32 character string. This is an 80 character string. Now, when the dim and param statements get built, this one and this one will get this modifier after the word string. This dim statement, or this one, will not. Okay, now that said, another real and another string are going to be dimensioned. Decode has no way of knowing they were dimensioned by use. It just knows they occurred in the I code area and they were valid variables. So what it's going to do is create dim statements for an R0011 and S0012. As the string variable will not get the string modifier because string without a modifier is a 32-character string. Okay. Now, if you use the naming convention for variables that I do, or something similar to it, this is how you'll know you have a defined by use string, because it will have a $ character after it, and none of the other strings will have a $ character. As for the real, the only clue you're going to have is that it was defined by use is that it occurs after the last valid variable. Okay? And it will be between the last variable and the parameter in this case. Okay? So that's the variables file that contains all of the information. Now in decode, these are two different tables, or well, they're two different things. They're related. One is an array that's held in memory. The other is a data file that contains the remainder of the information. It is those two things together that create these records. So when I create this output file, I am combining both of those records, the array record that's in memory and the file record that's on disk, into one record output. And that's how it works. So that's what I'm doing. Okay. So that brings me to the end of the notes, although I do need to add one other thing. Due to a discussion I had yesterday, and it seems to be continuing to some degree today, I've always had questions about how Basic09 stores the data that gets lost when a procedure is packed. I have always envisioned it to be three tables, one for variables, one for line numbers, one for everything else, or as I call it, comments. The variables, in my estimation, includes the name of the variable and the offset address that's the pointer to where that variable occurs, where it points to, either in data memory or to the description area or to the symbol table. Okay? And then the line numbers table contains the line number label, which in Basic09, while they are labels, they're all numbers. You can't have a on error go to error trap. It doesn't work. It has to be a line number. Okay? But the line number is, as you saw in the breakdown of the I code, just a label. A label saying, look for this address. Okay? So that's what I believe those two are, and I believe they're tables. The third one, I'm not sure if it's a table, more than one table, or any kind of table at all. The only thing I can be certain of is that it contains every comment, including the comments that are on a line with a statement. If there's a backslash character and then a comment token, it gets put, everything after the backslash then gets put in that comments table. It includes those, it includes blank lines, and it includes line numbers that were at the beginning of a statement that were not resolved with a goTo or a goSub or some other token that requires a line number. So that's what I believe is in that third table. Again, if it's a table and not more than one, if it's a table at all, whatever it is, it holds all that, because that's what gets lost. Okay? That and the line number labels and the variable names. Okay? I believe when it's packing the code, the first thing it does is it goes through, and every single line that is a comment, okay, gets removed first, and the offset address of the next instruction gets updated. Okay? If it's a variable, and there was a change, that variable reference gets updated, line number references get updated, and it does this each step through the code, resolving everything down so that there are no more variable names, no more line number references, no more comments, blank lines, or unused line number references. Okay. And so what ends up being packed is what remains, which is the rest of the I code. And I'm not sure if the description area and the symbol table exist as is, as they occur in the packed I code, in the unpacked code in Basic09. They may. One person has suggested that they do exist that way. I wouldn't be surprised, but I'm not sure. I know that the more tables they have, the more memory they're using, and those tables take up memory. So, and each module or each source file in the workspace has all of that, because each one is different. Each one has different variables, different line number references, different comments, and different blank lines, and different unused line number references. Okay? So each procedure in the workspace has its own set of these things. I would really like to know exactly what Basic09 keeps in memory before packing. And the reason for that is because I would like to see at some point if there is a way to modify Basic09 to save those tables out before destroying them. Because if I had access to that data, I could rebuild the source code and decode using your variable names, your line number references, and restoring all of your comments, blank lines, and unused line number references. Because it would all be there. But in order to do that, I need that data. So I need to know how Basic09 stores it, and how to add code that would save that data out before destroying it. And that would be probably a flag added to Basic09 where you do Basic09 dash this flag, and that tells it to save those files out. And each one could be named according to the name of the procedure with an extension that identifies which table it is. Okay? Yeah. And that way that data would be available, and I could use it to rebuild your source code exactly the way you had it written. Unfortunately, that will be of no use to procedures that were packed before that was able to be done, because if you lost the source code and you're using decode to get it back, those files don't exist. Yeah. So, but anyway, that's it for that. And I want to thank everybody for watching the video. If you've made it this far, thank you for staying until the end. And I'll see you in the next video.